So let's briefly see some applications in scalar quantum field theory. I mean, the scalar field theory, the thing that everyone starts with. And I'll, in homework, there will be the quantum mechanical case of the simple harmonic motion, or so to say, the simple harmonic oscillator. I'll give you a step-by-step derivation, and if you want, I can help you in, doing it. Yeah. So the free scalar field theory. What is a field? Well, for us, it's something that has some, for a scalar field, there is some sort of a value, in the space-time that you're dealing with. And for a scalar field, this is true for any point, like it has the same value and something like that. Or, this can be considered as a constant field, but just to avoid complications, just think of it as the following: phi of x is equals to phi prime of x prime. That means at any point in space-time, there is some sort of a value. This is that kind of field, some idealistic stuff. And the action for this kind of field is written as the follows. As follows. If you want to work in d dimension, you can write this. There are lots of conventions. I really don't want to dive into that right now. I'm just going to show you the thing that I usually do. There are tons of conventions like the metric, the sign of the metric, whether you are writing the Euclidean action or the real-time action, whatever. I'm not going to show that because it's going to confuse you a lot. So this is the action, and if you work in 4 dimensions or any dimension where there is only a single time direction, then you can decompose this thing as -1/2. And if the metric you choose is something like this, that means that you identify the time with a minus sign, then this one will go away, and you will have this phi dot squared -1/2 the gradient of phi whole squared -1/2 of m squared phi squared. So these are the spatial derivatives. This is the time derivative. Don't worry if you don't get any of this. Don't worry about it right now. So this is a a scalar field theory. By a scalar field theory, we mean the action, okay? And you can get the classical equations of motion by demanding this. This will be in homework. You're gonna have to, because you guys know how to take functional derivatives, right? Should I show it? This will be on homework, so maybe if you get stuck, you can contact me for the technical details. I'll try to help you with that as well. So if you take the functional derivative of s with respect to phi, that should give you the equation of motion for phi. And you can show that the equation of motion is nothing but delta phi is equals to 0, where this delta is given by this operator. This is a differential operator, this delta. Now, in quantum field theory, you take these classical fields and you try to quantize them, and that's where particles come in. When you quantize the fields, the quanta of those fields are your particles. So I'm not gonna go into any details of the canonical quantization. Just like quantum mechanics, there is some sort of a momentum associated with the field. You have the field that acts as a analogous to a position operator. You impose the canonical commutation relationship between them. You create then you define creation and annihilation operators and stuff like that. Then you go move on, just like simple harmonic oscillator. But in path integral, what people do is that they define this one thing I forgot to mention is that this expression over here, sometimes it is called a generating function null. because all the quantities of interest in a quantum field theory are generated from it. So maybe that's why they call it generating functional. I don't exactly know. So this is written as the path integral for the free scalar field theory. It's written as this dd of x. We're dealing with d dimensions, so let it be that way. This j can be thought of as a source term. And if you imply this source term in the classical action, that means over here, then your classical equation of motion would look something like this. This is like a equation in your electrodynamics. Like there is some sort of a field and there is some sort of a, source, a source charge or something like that. It's causing the particle to propagate in the field and stuff like that, interact with them. There are sources, there are sinks, and when we study topology, we'll get into that as well. So for now, think of this as a term that is almost analogous to your Maxwell equations. It's like a source current term and something like that. So this is how the path integral is written in quantum field theory. And again, these are your functional integral measures. What you can do right now is that you can use the classical action, that means this expression, you can put it over there, and then you can show that this z0 of j is equals to something like this. Z0 of 0 times integral of, let me write the exponential first. If I recall correctly, it should be some j delta inverse another j. I think Rakin gave you an exercise like this, right, in his random matrix theory course. So yeah, there should be a dd of x. I know I'm out of time, but I'm trying to make it as short as possible. I wrote all the details in the notes, like how you go from this line to this line. So if you are interested, you can see that. It's not mandatory for this course. If you're interested, you can see that, and if you get confused, you can ask me questions and stuff. So this is your e to the power I, and there is a 1/2 as well. Yeah, that's pretty much it. And this z0 of 0, this is just e of phi e to the power I s0, that means the classical action without any source term. Okay. And what does this subscript mean? This z0, this usually means the free theory. That means there are no interactions. The particles don't talk to each other. So you see that there are two generating functionals, and what people do is that from this expression you can understand the fact that this is like a normalizing factor, or the main quantity of interest should be z of z divided by z of 0. So people usually take it to be 1. This is a normalization convention. This is equals to 1. So finally you write your generating functional as, not this again, e to the power I by 2 dd of x j of x del inverse j of x. And let me show you what this del inverse is. It's pretty easy to find out. Del inverse is the inverse operator of this del, and together they give you some delta function. Okay, if it's on x, if it's on y, it should be delta x minus 1. And this is also known as the Feynman propagator, or the Green's function of this differential operator. Feynman propagator. How do you evaluate it? Pretty easy. You saw that the classical equation of motion was something like this. Are you guys alive?
Kind of, yes.
Barely.
Okay, understandable.
Barely.
Yeah, it's understandable. So this is a second order differential equation. You guys understand that, right? It might be multidimensional, but for our for the sake of understanding, let's make it one dimensional. Okay, this is familiar. You can do it, right? You understand this thing.
Yeah.
So this green function or the Feynman propagator is the inverse of this guy, this differential operator. Okay, so how do you compute it? Well, I'm not going to go into the details again because we are already past 6:30 and I need to finish it as soon as possible without killing you people. So yeah, so let me just show you how to find out the propagators, because this is easy. You should be able to do it. How to find out Feynman propagators. Actually, it's the generalized green function. Feynman propagator is when you integrate over the time dimension and stuff like that. So let me write Green's function instead of Feynman's propagator. Did you guys do any course on differential equations? Apart from Math 203, like differential equation
No.
2 and stuff?
না
Yeah.
ওয়ান করছিলাম, ওয়ানে কিছু করা হয়নি এগুলো।
Okay, fine. So the idea is to write this equation, but instead of 0, you put a delta function over there, like dx square plus m square phi of x some delta x minus y. Okay. Now it's pretty easy from here. You guys are familiar with Fourier transformations. Do a Fourier transformation. Whenever you are stuck on position space, Fourier transform and go to the dual basis. Some phi of, okay, let's not write it like this. I'm ignoring each and every kind of constant there is, like 1 upon 2 pi's and stuff. And even if you do that, they will just get cancelled anyways. So yeah, so this is what? This is e to the power minus I p x phi of p, and delta is what? E to the power px. Oh, there should be an integration as well. It should be integrated over p x minus y, right? So then use this differential operator on this guy. You have to differentiate under integration symbol. Integration is over p, differentiation is over x, so you are completely fine. If you do a second derivative, you should end up with minus I squared is just what? Minus 1. So you have a minus p square plus m square is equals to what do we have over here? E to the power minus I px some del p, something like this. dp, right?
সাই অফ পি থাকবে তো।
Oh, yeah. Okay, this is stuck again. Oh, okay. So from this part, can you see how we can get the propagator? Can you see? No, because you cannot. I mean, just give me one good reason. Why should I write a delta over here? Nobody saw that. That's why I was trying to mislead you guys as well. Like, just think of this. This is the same equation you wrote over there, right? So why put a delta now? That doesn't make any sense. Because I told you that the propagator or the Green's function is the inverse of this differential. So instead of phi, it should be the propagator itself, the tail inverse one. Nobody saw that, and I was pretending everything was fine, and everyone was like, oh, it's fine. So I know it's pretty late and you guys are already exhausted, but when you do this kind of things, it's very easy to get confused. So you have to be a bit more how to say this, focused on the details of what I am writing or what you are writing. Okay. So this thing that I wrote phi, that's completely wrong. This is not the thing. It's another equation where the source is a delta function. So to get the Green's function, you can write this as g or delta inverse 1, whatever you want, such that g times this delta, that means this differential operator, is the delta x minus y or something like that. Okay. Whew. So yeah, I mean, and if you are trying to solve for g, uh, then you can take these things out, you know, g of p. You differentiate these guys, you get rid of these integration symbols, right? There is integration on both sides, so you can get rid of them. There is this exponential guys, you can get rid of them as well. And usually on this side over here, usually people write this as x minus y, because in general, if you have something as a function of g of xy, it's a 2-point, it's also called a 2-point function as well. So you can write it as e to the power negative I p x minus y g of p, like this. So you get rid of all this, or what you can do if you want to be more concrete is that you take this integral on this side on a minus, then you factor out stuff, the integration measure the integral itself, like that. And what you have over here ultimately is that g of p is some 1 upon minus p square plus m square. And most of the time, if you're considering this from a physical point of view, this guy is divergent, so that's why people put an I epsilon over there to make things convergent. So when you study quantum field theory, this is also known as the I epsilon prescription, because the poles are on the real axis, and by special relativity, p square minus p square plus m square is equals to 0. I hope you guys know this. So that's how you find out the propagator, or so to say the Green's function. And once you find that out, you can take this generating functional. Let me write down that again. So now you have your propagators. Have your propagators for free field theory, for field theories. Let's call them delta inverse 1. Then you write the generating function now as e to the power I by 2 dd of x j of x. It should be delta x minus y, since this is a 2-point function, the propagator. I'm writing this as delta inverse 1, and this is now j of y. This is how it should be written properly. And now you can derive the 2-point correlation functions, let's say phi of x, phi of y. Graphically, this is something like this. Just a line. That means a particle is going from x to y. How this comes? Well, you just have to take the functional derivatives of it. And this line is just your propagator. That means a particle is getting created at x. It's going from x to y. And at space-time point y, it's going to get destroyed. That's what this 2-point function means. You can have a 3-point function, 4-point function, n-point function, and you can even have this, let's say, thing like this. This, if I'm not wrong, I don't remember it right now exactly. Let's call this x prime. This is x prime point. This is x. This is y. What this 4-point function means is that a particle is going from x to y, and at some point x prime, it's interacting with itself, you know. It seems a very very weird interaction, but this is a loop. You see these 2 points are equal, so at this point it's kind of interacting, I don't know, slapping itself or something like that, and after that it's going to y. So these are the stuff that you can easily do with path integrals. And when you do a course on quantum field theory, you will actually see how these things come up from the canonical point of view, and then you move to a advanced quantum field theory course or a quantum field theory 2 course, then you'll see this guy over here. In fact, what you can do, you can identify like which Feynman graphs are useful to you using this generating functionals, and that is given by some w of j, that is e to the power uh, was it e to the power I of j, yeah, or was it e to the power iw and j was over there, I don't exactly remember, but there are graphs in quantum field theory or Feynman diagrams in quantum field theory that are connected, and there are diagrams that are disconnected, and disconnected diagrams, they don't contribute anything. The only connected diagrams are relevant, and from there is another thing called an effective action, all sort of stuff. And all those formalisms, they use this path integral formalism, where you have to first write down something like this z of j, and ultimately you have to compute things like j of 1 delta j of 2, let's say the nth derivative of your z of z. It all boils down to your functional derivatives and stuff like that. So yeah, so even if you don't get all of this stuff that I babbled about, don't get worried. If you understand the computations of the kernel, you should be just fine. That was the main goal, and the rest of the things, they are just a part of your applications in quantum field theory and quantum mechanics and stuff like that. So I think I won't continue anymore. If you guys want to discuss about the Dirac field, we can discuss that later. Okay. And with this, I think I should conclude the discussion on path integrals. Now, if you have any questions so far, you can ask.
In the notes, I saw that this whole thing is like bosonic functionality.
Yeah, yeah, they're bosonic, like scalar fields, right?
Yeah. So like there for fermionic fields are also there.
Yeah, harmonic fields are also there. So there is not much difference. I'm sorry. Like, just give me 2 minutes, okay? It's really loud. Okay. Also, I think I should stop the recording, right? Should I stop the recording? Okay, bye. Okay,
Bye bye.
bye. আচ্ছা ঠিক আছে, bye.
Bike with them. Okay.